Hello. So we're going to be doing something different today. And I don't think we're going to be done. Well, I know we're not going to be done today. So this is going to be an ongoing project. The idea is to see if I can write a large language model from scratch. I've never done that before, and I don't have a background in AI or machine learning. What's going to happen is we're going to read through this textbook on neural networks by Michael Nielsen. I've read through it once years ago. So this part I should be able to have a jump start on. Then by the end of this, we're going to have the basic concepts for neural networks in the bag. And we're going to see if we can then learn how transformers work. So at the end of this book, we're going to be able to do handwriting recognition, digit recognition. This book does not cover convolutional neural networks. So the step after that, no, you know what? I don't think we need convolutional neural nets. I think transformers might be directly the step after this. Then if we can understand transformers, I think we can make large language models. I think that's all there is to it. But I don't know. That's the thing. So we're going to find out. But we're going to start with the basics of neural networks. So let's get going. I'm gonna just literally read this book. And anytime there's a concept that can be programmed, I'm gonna program it. And that's how I'm going to try to understand how neural nets work, and then we're gonna build from there. So that is the plan. Okay, so let's get going. Chapter 1. Using neural nets to recognize handwritten digits. The human visual system is one of the wonders of the world. Consider the following sequence of handwritten digits: 504192. Most people effortlessly recognize those digits as 504192. That ease is deceptive. In each hemisphere of our brain, humans have a primary visual cortex, also known as V1, containing 140 million neurons, with tens of billions of connections between them. And yet human vision involves not just V1, but an entire series of visual cortices, V2, V3, V4, and V5, doing progressively more complex image processing. We carry in our heads a supercomputer, tuned by evolution over hundreds of millions of years and superbly adapted to understand the visual world. Recognizing handwritten digits isn't easy. Rather, we humans are stupendously, astoundingly good at making sense of what our eyes show us. But nearly all of that work is done unconsciously, and so we don't usually appreciate how tough a problem our visual systems solve. The difficulty of visual pattern recognition becomes apparent if you attempt to write a computer program to recognize digits like those above. What seems easy when we do it ourselves suddenly becomes extremely difficult. Simple intuitions about how we recognize shapes, a 9 has a loop at the top and a vertical stroke in the bottom right, turn out to be not so simple to express algorithmically. When you try to make such rules precise, you quickly get lost in a morass of exceptions and caveats and special cases. It seems hopeless. Neural networks approach the problem in a different way. The idea is to take a large number of handwritten digits, known as training examples, and then develop a system which can learn from those training examples. In other words, the neural network uses the examples to automatically infer rules for recognizing handwritten digits. Furthermore, by increasing the number of training examples, the network can learn more about handwriting and so improve its accuracy. So while I've just shown 100 training digits above, perhaps we can build a better handwriting recognizer by using thousands or even millions or billions of training examples. In this chapter, we'll write a computer program implementing a neural network that can learn, or that learns to recognize handwritten digits. The program is just 74 lines long and uses no special neural network libraries. But this short program can recognize digits with an accuracy over 96% without human intervention. Furthermore, in later chapters, we'll develop ideas which can improve accuracy to over 99%. In fact, the best commercial neural networks are now so good that they are used by banks to process checks and by post office to recognize addresses. We're focusing on handwriting recognition because it's an excellent prototype problem for learning about neural networks in general. As a prototype, it hits a sweet spot. It's challenging, it's no small feat to recognize handwritten digits, but it's not so difficult as to require an extremely complicated solution or tremendous computational power. Furthermore, it's a great way to develop more advanced techniques such as deep learning. And so throughout the book, we'll return repeatedly to the problem of handwriting recognition. Later in the book, we'll discuss how these ideas may be applied to other problems in computer vision and also in speech, natural language processing, and other domains. Of course, if the point of the chapter was only to write a computer program to recognize handwritten digits, then the chapter would be much shorter, but along the way we'll develop many key ideas about neural networks, including two important types of artificial neuron, the perceptron and the sigmoid neuron, and the standard learning algorithm for neural networks, known as stochastic gradient descent. Throughout, I focus on explaining why things are done the way they are, and on building your neural network's intuition. That requires a lengthier discussion than if I just presented the basic mechanics of what's going on, but it's worth it for the deeper understanding you'll attain. Among the payoffs, by the end of the chapter, we'll be in a position to understand what deep learning is and why it matters. Perceptrons. What is a neural network? To get started, I'll explain a type of artificial neuron called a perceptron. Perceptrons were developed in the 1950s and 1960s by scientist Frank Rosenblatt, inspired by earlier work by Warren McCullough and Walter Pitts. Today it's more common to use other models of artificial neurons. In this book, and in much modern work on neural networks, the main neuron model used is one called the sigmoid neuron. We'll get to sigmoid neurons shortly, but to understand why sigmoid neurons are defined the way they are, it's worth taking the time to first understand perceptrons. So how do perceptrons work? A perceptron takes several binary inputs, x1, x2, etc., and produces a single binary output. In the example shown, the perceptron has three inputs, x1, x2, x3. In general, it could have more or fewer inputs. Rosenblatt proposed a simple rule to compute the output. He introduced weights, w1, w2, etc., real numbers expressing the importance of the respective inputs of the output to the output. The neuron's output, 0 or 1, is determined by whether the weighted sum over j, of wj times xj is less than or greater than some threshold value. Just like the weights, the threshold is a real number, which is a parameter of the neuron. To put it in more precise algebraic terms, output is equal to 0 if the sum of the weights times the inputs is less than or equal to threshold, equal to 1 if the sum of the weights times the inputs is greater than the threshold. That's all there is to how a perceptron works. Okay. So let's implement a perceptron. I'm going to make a directory for this project. I'll just call it LLM. And then we're going to we're going to make perceptron.py. Def perceptron. It takes a bunch of x's as input, so x. Yeah, it takes a variable number of x's as input. It has a bunch of weights. And it returns either a 0 or a 1, so let's have it return a Boolean. So here. Return. I guess it needs a bunch of W's, so let's make this a, I guess we'll make this a class perceptron. When you initialize it, you have to give it its weights. Self.w equals w. Which is going to be a list of floats. And then when you apply it, you have to pass in the x. Return. I basically want, I have to do this multiplication, so I'm gonna do for I in range len of self.w. We've got a total, so total equals 0. Total plus equals self.w at I times x at I. Return total is greater than threshold, so we also needed threshold up here. Self.threshold. So that's our perceptron. Let's try it on some test cases. Perceptron, so P equals perceptron. I actually don't know if this will work. Let's say 0.2, 0.2, 0.2, threshold equals 0.5. Is this allowed? I guess this would have to be a list. But then, oh, and this should not be an int, this should be a float. Why, or how do I, what did having the star here do? I guess it didn't do anything. List of float. P.apply, and then we're gonna have 0.5, 0.5, 0.5. Print result. Python perceptron. So if I just print out the total here as a intermediate thing, Yeah, so each of the 0.2s gets multiplied by a 0.5, and that does not meet the threshold. If our threshold were lower, then it would meet the threshold. So we've got a perceptron here. It looks like this is working properly. Cool, so let's get back to the book. That's the basic mathematical model. A way you can think about the perceptron is that it's a device that makes decisions by weighing up evidence. Let me give an example. It's not a very realistic example, but it's easy to understand, and so we'll get more realistic examples. And soon we'll get more realistic examples. Suppose the weekend is coming up and you've heard that there's going to be a cheese festival in your city. You like cheese and are trying to decide whether or not to go to the festival. You might make your decision by weighing up 3 factors. Is the weather good? Does your boyfriend or girlfriend want to accompany you? Is the festival near public transit? You don't own a car. We can represent these 3 factors by corresponding binary variables x1, x2, x3. For instance, we'd have x1 equals 1 if the weather is good. Let's copy the example here and make sure we're getting the right answer. X1 equals 0 if the weather is bad. Similarly, x2 equals 1 if your boyfriend or girlfriend wants to go, and x2 equals 0 if not, and similarly again for x3 and public transit. Now suppose you absolutely adore cheese, so much so that you're happy to go to the festival even if your boyfriend or girlfriend is uninterested and the festival is hard to get to. But perhaps you really loathe bad weather and there's no way you'd go to the festival if the weather is bad. You can use perceptron to model this kind of decision making. One way to do this is to choose weight W1 equals 6 for the weather, W2 equals 2, and 2 for the other conditions. The larger value of W1 indicates that the weather matters a lot to you, much more than whether your boyfriend or girlfriend joins you, or the nearness of public transit. Finally, suppose you choose a threshold of 5 for the perceptron. So, threshold 5. With these choices, the perceptron implements the desired decision-making model, outputting 1 whenever the weather is good and 0 whenever the weather is bad. It makes no difference to the output whether your boyfriend or girlfriend wants to go or whether the public transit is nearby. Let's confirm that. So, this means weather good and the other things are bad. We said true, which means we do want to go. If the weather were bad, but our boyfriend wanted to go and the public transit was good, we would say false. Okay. By varying the weights and the threshold, we can get different models of decision making. For example, suppose instead we chose a threshold of 3. Then the perceptron would decide that you should go to the festival whenever the weather was good, or when both the festival was near public transit and your boyfriend or girlfriend was willing to join you. So threshold 3. So we want to go even though the weather is bad. If only public transit is good, then we don't want to go. If the weather's good, we do want to go. What if the weather's good and our boyfriend doesn't want to go? We still want to go. Okay, so it's a little... With a threshold of 3, the other 2 things have to be true if the weather is bad. In other words, it'd be a different model of decision making. Dropping the threshold means you're more willing to go to the festival. Obviously, the perceptron isn't a complete model of human decision making. But what the example illustrates is how a perceptron can weigh up different kinds of evidence in order to make decisions, and it should seem plausible that a complex network of perceptrons could make quite subtle decisions. In this network, the first column of perceptrons, what we'll call the first layer of perceptrons, is making 3 very simple decisions by weighing the input evidence. What about the perceptrons in the second layer? Each of these perceptrons is making decisions by weighing up the results from the first layer of decision making. In this way, a perceptron in the second layer can make a decision at a more complex and more abstract level than perceptrons in the first layer. And even more complex decisions can be made by the perceptron in the third layer, the one perceptron in the third layer. In this way, a many-layer network of perceptrons can engage in sophisticated decision-making. Incidentally, when I defined perceptrons, I said that a perceptron is just a single output. In the network above, the perceptrons look like they have multiple outputs. In fact, they're still single output. The multiple output arrows are merely a useful way of indicating that the output from a perceptron is being used as the input to several other perceptrons. It's less unwieldy than drawing a single output line, which then splits. Let's simplify the way we describe perceptrons. The condition sum over j of wj times x times j greater than threshold is cumbersome, and we can make two notational changes to simplify it. The first change is to rate sum over j of wj times xj as a dot product. W dot x is defined as being equal to sum over j of wj times xj, where w and x are vectors whose components are the weights and inputs respectively. The second change is to move the threshold to the other side of the inequality and to replace it by what's known as the perceptron's bias, b defined as being equal to negative threshold. Using the bias instead of the threshold, the perceptron rule can be rewritten. Output equals 0 if w time dot x plus b is less than or equal to 0, 1 if w dot x plus b is greater than 0. So let's make that change. So instead of holding a threshold, we're going to hold a bias. Instead of checking if we're greater than a threshold, we're going to check if this plus bias is greater than 0. Yep, it's apart from that, it's the same. This is a dot product, but let's use the opportunity to switch to using NumPy. So I'm going to make a virtual environment here, python-m venv. This is saying use the venv module to make a virtual environment called venv. So I now I now have a venv folder in here. Let's activate the virtual environment, source venv bin activate. So now I'm in the virtual environment. Now if I take a look at what I'm running when I run Python and when I run pip, it's the versions of Python and pip inside the virtual environment. So now I can install stuff and it'll just install it for this folder in this virtual environment. So pip install NumPy. All right, we have NumPy, which means I should be able to do from NumPy import np. Oops, yes. np dot here. I just don't want my linter to remove np because it's not being used, so I'll just print np here. It's being underlined. That's because I'm not using the virtual environment from inside. I'm not using the Python from inside this virtual environment. So if I switch to this, now it should know what NumPy is. Oh, and obviously this is not how you do it. You do import NumPy, and then whenever people import NumPy, they usually rename it np. I guess just because it saves a few characters when you're typing it. Okay, now we want to use NumPy to do a dot product instead of looping over the components ourselves. So we're gonna have to make vectors out of these lists of floats, which I don't really know how to do. I know that I know a few ways to do it. I don't know why you would do it one way versus another. So instead of a list of floats, I'm going to say that W is a ND array, which is a data type. That means like an array in NumPy. I actually, maybe we should look this up. NumPy ND array. Fundamental data structure for n-dimensional arrays. Okay, so when you do dot array, the type is an ND array. So that's why you, so I should put ND array in my type signature, but I should just call np.array when I'm initializing it. So this will be np.array. And we'll do the same here. So you should be a ND array. Okay. Now we want to use a dot product. So numpy dot product. How do you do that? Numpy dot dot. Cool. So instead of doing all of this stuff, we're just going to do np dot dot wx. Self.wx. Now, are we getting the same results as before? Python perceptron. This is true. This should be false, but it's true. Okay, so let's print the intermediate values. Print the dot product, print self.bias. Oh, the bias is supposed to be the negation of the threshold. So I should have said -3 here. Okay, so now this says false. This should say true. It does. And this should say true. It does. Okay, so we've replaced, we've successfully re-implemented this as using the new notation, using NumPy to do the dot product. You can think of the bias as a measure of how easy it is to get the perceptron to output a 1. Or to put it in more biological terms, the bias is a measure of how easy it is to get the perceptron to fire. For a perceptron with a really big bias, it's extremely easy for the perceptron to output a 1. But if the bias is very negative, then it's difficult for the perceptron to output a 1. Obviously, introducing the bias is only a small change in how we describe perceptrons, but we'll later see that it leads to further notational simplifications. Because of this, in the remainder of the book, we won't use the threshold, we'll always use the bias. I've described perceptrons as a method for weighing evidence to make decisions. Another way perceptrons can be used to compute the elementary logical functions we usually think of as underlying computation. functions such as AND, OR, and NAND. For example, suppose we have a perceptron with two inputs, each with a weight -2 and an overall bias of 3. Here's our perceptron. Okay, let's implement it before we read forwards. So perceptron with weights -2 and -2 and a bias of 3. Result equals p.apply np.array 0, 0. Actually, let's print the whole truth table. Print 0, 0 maps to this, and then 0, 1, 1, 0, 1, 1. True, 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 false. So this is computing NAND. This is computing NAND because it's only true. It's only false when the AND would have been true. So it's the opposite of AND. We can see that input 0, 0 produces output 1, since -2 times 0 plus -2 times 0 equals +3 equals 3, or +3 equals 3 is positive. Here I've introduced the star symbol to make the multiplication explicit. Similar calculations show that the inputs 0, 1 and 1, 0 produce output 1, but the input 1, 1 produces output 0, since -2 times 1 plus -2 times 1 plus 3 equals -1 is negative, and so our perceptron implements a NAND gate. The NAND example shows that we can use perceptrons to compute simple logical functions. In fact, we can use networks of perceptrons to compute any logical function at all. The reason is that the NAND gate is universal for computation. That is, we can build any computation up out of NAND gates. For example, we can use NAND gates to build a circuit which adds 2 bits, x1 and x2. This requires computing the bitwise sum x1 bit sum x2, as well as a carry bit which is set to 1 when both x1 and x2 are 1, i.e. the carry bit is just the bitwise product x1 times x2. So this is called a half adder, or maybe it's called a full adder. It's called half or full depending on whether it handles carry bits. And this one is handling a carry bit output, but not a carry bit input. Anyway, when you make a CPU out of NAND gates, full adders and half adders are like the first thing that you try to make. So he's just showing that if a perceptron can make a NAND gate can make circuits for doing stuff like addition. They can also make any other kind of circuit. So you can do any computation with a perceptron is what he's trying to show. To get an equivalent network out of perceptrons, we replace all the NAND gates by perceptrons with 2 inputs, each with weight -1 and an overall bias of 3. Here's the resulting network. Note that I've moved the perceptron corresponding to the bottom right NAND gate a little, just to make it easier to draw the arrows on the diagram. One notable aspect of this network of perceptrons is that the output from the leftmost perceptron is used twice as input to the bottommost perceptron. When I defined the perceptron model, I didn't say whether this kind of double output to the same place was allowed. Actually, it doesn't much matter. If we don't want to allow this kind of thing, then it's possible to simply merge the 2 lines into a single connection with a weight of -4 instead of 2 connections with -2 weights. If you don't find this obvious, you should stop and prove to yourself that this is equivalent. Okay, time for us to stop and prove to ourselves something. So if we don't want this guy to have the same output, to have the output of the previous perceptron be duplicated, we could have just a single input with a weight of -4 instead of 2 with a weight of -2. Yeah, that makes sense because this is working on binary numbers, so the only possible inputs are 0 and 1. If the input which is duplicated is 0, then the output's gonna the answer is gonna be the same whatever the weight is. If the input is 1, then by doubling the weight, that's the same as multiplying by half the weight twice, and then yeah, it's just saying like you can times 2 it instead of times 2ing it by having 2 inputs, you times 2 it by multiplying it by 2. With that change, the network looks as follows, with all unmarked weights equal to -2, all biases equal to 3, and a single weight of -4 as marked. Okay. So I could implement this. I don't think it's that helpful because I don't think this is a stepping stone to the next thing. This is just an example that they're giving. So I happen to know that already, which is why I know that that's why I think that I don't have to implement this just to understand it. All right. Up to now, I've been drawing inputs like x1 and x2 as variables floating to the left of the network of perceptrons. In fact, it's conventional to draw an extra layer of perceptrons, the input layer, to encode the inputs. So it's just putting circles around the inputs here and calling them an input layer of perceptrons. Or I guess they're not of I guess they are of perceptrons. This notation for input perceptrons, in which we have an output but no inputs, is a shorthand. It doesn't actually mean a perceptron with no inputs. To see this, suppose we did have a perceptron with no inputs, then the weighted sum over j of wj times xj would always be 0, and so the perceptron would output 1 if b is greater than 0, and 0 if b is less than or equal to 0. That is, the perceptron would simply output a fixed value, not the desired value, x1 in the example above. It's better to think of the input perceptrons as not really being perceptrons at all, but rather special units which are simply defined to output the desired values, x1, x2, etc. Okay, so they're not perceptrons. Not sure why we even label them as though they are perceptrons. The adder example demonstrates how a network of perceptrons can be used to simulate a circuit containing many NAND gates, and because NAND gates are universal for computation, it follows that perceptrons are also universal for computation. The computational universality of perceptrons is simultaneously reassuring and disappointing. It's reassuring because it tells us that networks of perceptrons can be as powerful as any other computing device, but it's also disappointing because it makes it seem as though perceptrons are merely a new type of NAND gate. That's hardly big news! However, the situation is better than this view suggests. It turns out that we can devise learning algorithms which can automatically tune the weights and biases of a network of artificial neurons. This tuning happens in response to external stimuli without direct intervention by a programmer. These learning algorithms enable us to use artificial neurons in a way which is radically different to conventional logic gates. Instead of explicitly laying out a circuit of NAND and other gates, our neural networks can simply learn to solve problems, sometimes problems where it would be extremely difficult to directly design a conventional circuit. Sigmoid neurons. Learning algorithms sound terrific, but how can we devise such algorithms for a neural network? Suppose we have a network of perceptrons that we'd like to use to learn to solve some problem. For example, the inputs to the network might be the raw pixel data from a scanned handwritten image of a digit. And we'd like the network to learn weights and biases so that the output from the network correctly classifies the digit. To see how learning might work, suppose we make a small change in some weight or bias in the network. What we'd like is for this small change in the weight to cause only a small corresponding change in the output from the network. As we'll see in a moment, this property will make learning possible. Schematically, here's what we want. Obviously, this network is too simple to do handwriting recognition. So you've got a network of perceptrons, or of maybe they'll be sigmoids instead of perceptrons. He's highlighting a specific arrow with a weight, W, and he's saying let's add a small change to that, so W plus delta W. Small change in any weight or bias causes a small change in the output, so then the output should be output plus delta output. Where if delta W is small, then delta output should also be small. If it were true that a small change in a weight or bias causes only a small change in output, then we could use this fact to modify the weights and biases to get our network to behave more in the manner we want. For example, suppose the network was mistakenly classifying an image as 8 when it should be a 9. We could figure out how to make a small change in the weights and biases so that the network gets a little closer to classifying the image as a 9. Then we'd repeat this, changing the weights and biases over and over to produce better and better output. The network would be learning. The problem is that this isn't what happens when our network contains perceptrons. In fact, a small change in the weights or bias of any single perceptron in the network can sometimes cause the output of that perceptron to completely flip, say from 0 to 1. That flip may then cause the behavior of the rest of the network to completely change in some very complicated way. So while your 9 might now be classified correctly, the behavior of the network on all other images is likely to have completely changed in some hard to control way. That makes it difficult to see how to gradually modify the weights and biases so that the network gets closer to the desired behavior. Perhaps there's some clever way of getting around this problem, but it's not immediately obvious how we can get a network of perceptrons to learn. We can overcome this problem by introducing a new type of artificial neuron called a sigmoid neuron. Sigmoid neurons are similar to perceptrons, but modified so that small changes in their weights and bias can cause only a small change in their output. That's the crucial fact which will allow a network of sigmoid neurons to learn. So it sounds like the problem with the perceptron is that the output is either exactly 0 or exactly 1. Which means a small change can cause it to flip, which could have cascading consequences in the rest of the network. So I think the important part of the sigmoid that we're going to see is that the output's not Boolean. Okay, let me describe the sigmoid neuron. We'll depict sigmoid neurons the same way we depicted perceptrons. x1, x2, x3 goes into the neuron, and then there's an output. Just like a perceptron, the sigmoid neuron has inputs, x1, x2, etc. But instead of being just 0 or 1, these inputs can also take on any values between 0 and 1. So I guess I jumped the gun a little bit because my perceptron inputs could also do that. I didn't force my perceptron inputs to be Booleans. They were already able to be any number. Okay, so for instance, 0.638 is a valid input for a sigmoid neuron. Just like a perceptron, the sigmoid neuron has weights for each input, W1, W2, etc., and an overall bias B, but the output is not 0 or 1. Instead, it's sigmoid of W dot X plus B, where sigmoid is called the sigmoid function and is defined by sigmoid of Z is defined as 1 over 1 plus e to the negative Z. To put it all a little more explicitly, the output of a sigmoid neuron with inputs x1, x2, etc., weights w1, w2, etc., and bias B is 1 over 1 plus x of negative sum of over j of wj times x of j minus b. Okay, let's start implementing. So touch or z sigmoid.py. Let's give it the same interface as perceptron. Call it sigmoid. Sigmoid. So you still take this value, but then you put it into a different expression. You don't just compare it to 0. So you take this part, we'll call that Z, and then you return sigmoid of Z. And now let's def sigmoid is equal to, or of Z, which is a float, and that returns a float. Return 1 over 1 plus e to the negative Z. So power of e negative Z. And from math import e. Yeah, there you go. What's wrong with this? Float is not assignable to return type bool. True, because this is a float now. Okay, let's try that out. Python sigmoid. Look at that. So this same circuit as a perceptron, the same weights and biases and inputs in a perceptron would have said true, 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 false. So the ones that are above 0.5, it looks like, perceptron would have said those are 1, and the ones that are below 0.5, perceptron would have said those are 0, but the sigmoid is blurrier. So it should have this property where if I change the input a little bit, so let's say 0.1 here, it changes the output only a little bit. So 0.94, 0.95, good. At first sight, sigmoid neurons appear very different to perceptrons. The algebraic form of the sigmoid function may seem opaque and forbidding if you're not already familiar with it. In fact, there are many similarities between perceptrons and sigmoid neurons, and the algebraic form of the sigmoid function turns out to be more of a technical detail than a true barrier to understanding. To understand the similarity of the perceptron model, suppose Z, defined as w.x plus b, is a large positive number. Then e to the negative z is approximately 0, so sigmoid of z is approximately 1. In other words, when z equals w.x plus b is large and positive, the output from the sigmoid neuron is approximately 1, just as it would have been for a perceptron. And that's what we are seeing here. Suppose, on the other hand, that z equals w.x plus b is very negative, then e to the negative z tends towards infinity, and sigmoid of z is approximately equal to 0. So when z equals w dot x plus b is very negative, the behavior of a sigmoid neuron also closely approximates a perceptron. It's only when w dot x plus b is of modest size that there's much deviation from the perceptron model. What about the algebraic form of sigma? Of sigmoid? How can we understand that? In fact, the exact form of sigmoid isn't so important. What really matters is the shape of the function when plotted. Here's the shape. The shape is a smoothed out version of a step function. If sigmoid had in fact been a step function, then the sigmoid neuron would be a perceptron, since the output would be 1 or 0 depending on whether w dot x plus b was positive or negative. By using the actual sigmoid function, we get, as already implied above, a smoothed out perceptron. Indeed, it's the smoothness of the sigmoid function that is the crucial fact, not its detailed form. The smoothness of sigmoid means that small changes delta wj in the weights and delta b in the bias will produce a small change delta output in the output from the neuron. In fact, calculus tells us that delta output is well approximated by delta output is approximately equal to sum over j of the derivative of output with respect to j times delta wj plus the derivative of output with respect to b times delta b, where the sum is over all the weights wj, and del output over del wj and del output over del b denote partial derivatives of the output with respect to wj and b respectively. Don't panic if you're not comfortable with partial derivatives. While the expression above looks complicated with all the partial derivatives, it's actually saying something very simple, and which is very good news. Delta output is a linear function of the changes delta wj and delta wb in the weights and biases. This linearity makes it easy to choose small changes in the weights and biases to achieve any desired small change in the output. So while sigmoid neurons have much of the same qualitative behavior as perceptrons, they make it much easier to figure out how changing the weights and biases will change the output. There was a footnote here that I don't want to miss. Actually, when w dot x plus b equals 0, the perceptron outputs 0, while the step function outputs 1. So strictly speaking, we need to modify the step function at that one point, but you get the idea. Okay. Okay, so that doesn't really matter. So can I understand this thing? I'm also not so comfortable with partial derivatives. The change in the output is approximately something times the change in the weight plus something times the change in the bias. I think that's the point, is don't worry about what this something is. The point is it's linear in the change of the bias and the weight. Okay. If it's the shape of sigmoid which really matters and not its exact form, then why use the particular form used for sigmoid in equation 3? In fact, later in the book, we will occasionally consider neurons where the output is f of w dot x plus b for some other activation function f. The main thing that changes when we use a different activation function is that the particular values for the partial derivatives in equation 5 change. This is equation 5. It turns out that when we compute those partial derivatives later, using sigmoid will simplify the algebra simply because exponentials have lovely properties when differentiated. In any case, sigmoid is commonly used in work on neural nets, and the activation function we'll use most often in this book. Okay, so this function here is called an activation function. They're saying or he's saying that this part is important, this part is not so important, and you can swap it out with different activation functions. And the only reason we're using sigmoid is that it's gonna be useful later when we're doing derivatives. How should we interpret the output from a sigmoid function? Obviously, one big difference between perceptrons and sigmoid neurons is that sigmoid neurons don't just output 0 or 1, they can serve as output, they can have as output any real number between 0 and 1. So values such as 0.173 and 0.689 are legitimate outputs. This can be useful, for example, if we want to use the output value to represent the average intensity of the pixels in an image input to a neural network. But sometimes it can be a nuisance. Suppose we want the output from the network to indicate either the input image is a 9 or the input image is not a 9. Hot dog, not hot dog. Obviously, it'd be easiest to do this if the output was a 0 or a 1, as in the perceptron. But in practice, we can set up a convention to deal with this. For example, by deciding to interpret any output of at least 0.5 as indicating a 9 and any output of less than 0.5 as indicating not a 9. I'll always explicitly state when we're using such a convention, so it shouldn't cause any confusion. Exercises. Sigmoid neurons simulating perceptrons, part 1. Suppose we take all the weights and biases in a network of perceptrons and multiply them by a positive constant c greater than 0. Show that the behavior of the network doesn't change. We take all the weights and biases, so let's go back to perceptron. We take all the weights and biases and multiply them by a positive constant c. So let's run Python perceptron. Let's validate this experimentally first. So c equals 99. Am I allowed to do this? 99 times array? Or wait, I meant to do c times array, c times 3. I get the same answers. It has to be a positive constant, so 9999999. It's the same answers for this example. Why is that? Well, it's because the constant is going to be on both sides of the of this thing, right? It's so if you multiply all of the weights, then you can extract the constant. Like if each w is multiplied by c, you can think of that as this whole vector multiplied by c. Or sorry, not the whole, you can think of that as this whole vector multiplied by c, which means you can pull it out of the dot product. So this is just going to be c times dot product plus c times bias. So now we can just take the c out from both sides and say this, which is not going to change the answer because c is positive, and so we're still going to be either positive or negative. So the comparison with 0 is not going to change. So yeah, because c is the same on the biases and the weight, or on the weights and the bias, it cancels out basically, as long as it's positive. I'm not sure why it being positive matters, but we did show that the behavior doesn't change. Part 2. Suppose we have the same setup as the last problem, a network of perceptrons. Suppose that the overall input to the network of perceptrons has been chosen. We don't need the actual input value, we just need the input to have been fixed. Suppose the weights and biases are such that w.x plus b is not equal to 0. for the input x to any particular perceptron in the network. Now replace all the perceptrons in the network by sigmoid neurons and multiply the weights and biases by a positive constant c greater than 0. Show that in the limit as c tends to infinity, the behavior of this network of sigmoid neurons is exactly the same as the network of perceptrons. How can this fail when w dot x plus b equals 0 for one of the perceptrons? Okay, so the input is fixed. Now we're doing the same thing we were doing here. We're multiplying by a c, and we're saying the sigmoid should become closer and closer to the perceptron. So let's test it. Weights times c. Bias times c. Python sigmoid. Now let's ramp up c and see that these things get closer to being a sigmoid. So 2, 5. We're already almost there. 0.99 for these, 0.00 for these. 99, 1.0, basically 0. And then we get some kind of division by 0 type deal. So if C is only 99, we get basically exactly equal to a sigmoid. So that's experimentally, but what is the reason? Show that in the limit as c tends to infinity, the behavior of this network of sigmoids, of sigmoid neurons is exactly the same. So, if you've got if you're multiplying the weights and the bias by c, then you basically have this whole expression multiplied by c, which means you're basically doing c times z in here. So if I remove this, but I keep the c times z up here, I think we're gonna see the same result. Yeah, so this is equivalent to doing c times z. Which means we're taking, if z is positive, we're making it close to infinity. If c is negative, we're making it close to negative infinity. Then if you look at this graph, close to infinity, you're 1, close to negative infinity, you're 0. That's how sigmoids work. So that's why if you multiply the input by a big number, it becomes closer to being a step function. Okay, cool. So that's going to be it for now. We're going to keep going at this in the next stream. But thanks for watching.